Internal combustion engine cars are unequivocally on their way out, perhaps not today, and maybe not in the immediate future, but eventually. As more and more nations move to ban emission-producing vehicles, the game will be over, to put it another way. EVs are the long-term bet for the planet, even with their current higher price tags compared to ICE vehicles. But what makes EVs so costly? And why is there still so much resistance against them? The answer is quite clear. The batteries can represent close to 40% of an EV's total cost. And at present, the vast majority of these batteries are based on lithium. In fact, roughly 75% of electric vehicles on the road today are powered by lithium batteries. But here is the stark reality. For many years, the world has operated under the dominance of lithium-ion. It is ubiquitous. It's not just in EVs, it's in your smartphone, your TV remote, and your children's toys. It's all powered by lithium. However, believe it or not, a major shift is on the horizon. In the near future, lithium could be entirely phased out, at least within the EV sector. The reason? A multitude of new battery chemistries are under development across the world, all sharing a single objective: to dethrone lithium. And if you're not a fan of Tesla, you should prepare yourself, because what comes next will likely intensify that feeling. Yet again, Tesla is on the verge of releasing a battery that could revolutionize the industry. We are talking about a technology with nearly 3 times the energy density of their current batteries. Very few people are aware of what has just transpired at Tesla, but this new battery could completely reshape the company's trajectory. And it could very well be Elon Musk's most significant gamble to date. How much power does it hold? How inexpensive could it become? Let's dive in. This new generation of batteries has clearly been under development at Tesla for a considerable time. While the company has attempted to maintain secrecy, internal leaks have signaled that Tesla wants the world to know they are making a massive push in EV battery tech, particularly for the affordable model slated for release soon. What is truly astonishing is that this new battery is composed of materials that are significantly more abundant and cheaper than lithium. Despite this, it provides 3 times the energy density of today's lithium-ion batteries naturally. New technology is flawless from the start. A few challenges still need to be addressed, but on the whole, this battery is already superior in almost every aspect. And as soon as those final hurdles are cleared, it won't just be a competitor to lithium. It has the potential to replace it completely, bringing an end to the era of lithium for good. Yes, we are talking about the Tesla A1 battery, the company's inaugural aluminum-ion battery. In simple terms, aluminum-ion batteries function similarly to lithium-ion batteries, but they use aluminum ions as charge carriers instead of lithium ions. Every aluminum-ion cell consists of 3 primary parts: anode, typically crafted from aluminum metal, which is the source of the aluminum ions; a cathode, constructed from materials like graphene or various metal oxides designed to house those ions; an electrolyte, a liquid medium that enables the aluminum ions to travel between the 2 electrodes. The fundamental difference is rooted in the nature of aluminum itself. Each aluminum ion has a triple positive charge, whereas a lithium ion has only a single charge. This signifies that aluminum can transport 3 times the energy per ion, dramatically increasing energy density without needing rare earth materials or complex production methods. In principle, this enables aluminum-ion batteries to hold much more energy within the same mass when compared to conventional lithium-ion batteries. And now, real-world data is beginning to validate that potential. Sources indicate that the aluminum-ion battery tech being tested by Tesla has now achieved energy densities exceeding 700 watt-hours per kilogram, a figure potent enough to utterly disrupt the entire battery market. To give you some context, if you were to put this battery in a Tesla, it could drive for over 700 miles. That translates to about 1,126 kilometers on one charge. Some projections even suggest that number could approach 1,000 miles, or roughly 1,600 kilometers per charge. This is a leap so profound that even the most bullish EV supporters would find it hard to accept. This brings up a major question: how did Tesla achieve such a massive technological breakthrough? A straightforward comparison highlights the difference. Currently, a Tesla Model 3 long-range AWD gets about 346 miles from a 79 kilowatt-hours NMC battery. Those NMC cells possess an energy density of only about 180 to 200 watt-hours per kilogram. But aluminum-ion batteries, they reach approximately 700 watt-hours per kilogram. That's about 3.5 times greater. What are the implications? If you were to replace the Model 3's NMC battery with an aluminum-ion pack of the same weight, the car could theoretically achieve around 1,038 miles, over 1,600 kilometers. On a single charge, this isn't just exceeding current benchmarks. It's rewriting the rulebook for the whole EV sector. And while lithium-ion batteries are still the standard today, as noted earlier, they haven't experienced a truly revolutionary jump in energy density in decades. Lithium-ion has been stagnating at around 200 watt-hours per kilogram for years, even with Tesla's most advanced efforts. Their 4,680 cells have only managed to increase energy density to about 275 watt-hours per kilogram, which is not enough to be a true game-changer. And that is precisely why an opportunity exists for something new, and aluminum-ion is emerging as one of the most promising contenders we have seen. With that said, we must be realistic. While aluminum-ion batteries can achieve 700 watt-hours per kilogram at the cell level, that figure decreases once you assemble a complete battery pack with its casing, cooling apparatus, and athernicary hardware. This is why optimizing the pack's design is so vital. It is the secret to maintaining high performance while simultaneously reducing manufacturing costs. So, instead of a theoretical 1,000-mile range, a more practical estimate would be nearer to 700 miles, but frankly, that is still more than enough to leave everything else on the market in the dust. Now, consider Tesla's 4,680 battery. It remains one of the most sophisticated battery technologies available. But there's a problem. This remarkable battery is currently found only in premium vehicles. It's essentially confined to the Cybertruck, where the least expensive model begins at $69,990. This poses a significant question: can Tesla integrate this technology into more affordable vehicles like the Model 3 or Model Y in the near future? The answer, for now, appears to be a firm no. The logic is simple: lithium prices are continually climbing, causing battery production costs to balloon, since all-Tesla's existing batteries LFP, NMC, and the 4,680 are still heavily dependent on lithium. Using the 4,680 in cheaper models is essentially a fantasy. Elon Musk has generated a lot of buzz about launching a compact EV for about $25,000. But in reality, that project has been stalled for over 4 years. Rumor has it that it's finally coming this November. Unsurprisingly, Tesla will almost certainly use LFP batteries for that vehicle. While an energy density of 700 watt-hours per kilogram is undeniably impressive, it is not the sole reason for Tesla's deep commitment to aluminum-ion battery technology. As Elon Musk himself has noted, the larger issue is the continuously rising cost of lithium-ion batteries. This is primarily because of the surging demand for lithium against a limited supply, which has resulted in overmining and constantly increasing prices. This has not only squeezed the entire EV industry but has also made it challenging for manufacturers like Tesla to offer more affordable models to the public. So, the price of lithium and all the base materials for the battery cells went sky high. It doubled. The price of cells doubled. The price of lithium, I think, went up almost fivefold. Like 500%, it just went up by insane numbers. Currently, Tesla employs LFP and NMC batteries for the Model 3 and Model Y, while the Cybertruck uses the 4,680 cells. All three depend on lithium and also utilize expensive materials like nickel and cobalt. A brief online search will confirm that these are among the most costly materials in battery manufacturing. Even Elon Musk has conceded that the 4,680 batteries are more expensive than conventional ones, because they are filled with all three: nickel, cobalt, and lithium. Therefore, despite the 4,680 being cutting edge, its cost remains a significant barrier preventing Tesla from installing it in more mainstream models. If you have any knowledge of metals in the Earth's crust, you'll know that aluminum is the most plentiful. It constitutes about 8.13% of the crust. Bauxite, the primary ore for producing aluminum, is located in dozens of countries, with worldwide reserves estimated at 1.59 billion tons. Aluminum is not only much easier to obtain than lithium, nickel, or cobalt, but it's also far less exposed to geopolitical tensions or supply chain breakdowns, and this presents a golden opportunity for Tesla to reduce battery costs dramatically. Based on available data, aluminum-ion batteries could cost as little as $40 to $65 per kilowatt-hour once the technology reaches full-scale commercialization. This figure could decrease even more if Tesla accelerates large-scale manufacturing, a feat they have already demonstrated with their huge battery operations at the Nevada Gigafactory. Of course, Tesla does not regularly share details on its production costs and has never officially stated the real cost of its batteries. However, according to independent analysis, it's believed that batteries typically make up 25% to 40% of a Tesla's total manufacturing cost based on the battery chemistry, car model, and configuration. For instance, with a Tesla Model Y priced from $45,000 to $60,000, its battery pack costs somewhere between $9,300 and $11,400. Assuming an average NMC battery cost of about $139 per kWh. This is equal to 19 to 25% of the car's total price. But if it were replaced with aluminum-ion batteries priced at just $40 to $65 per kWh, that cost would plummet to only $2,700 to $5,300. This implies Tesla could drastically lower its selling prices, opening a genuine path to making affordable EVs accessible to a wider audience. When Elon Musk decides to back a new battery technology, performance and energy density are always key considerations. But the single most important factor is scalability. Regardless of a battery's power, if it is too costly and only fits into luxury cars, it won't bring about meaningful change. This is why aluminum-ion batteries are anticipated not just to provide superior performance but also to crack the production cost problem, a critical element in allowing Tesla to reduce EV prices and move beyond its image as a brand that only sells cars for the affluent. Furthermore, aluminum-ion batteries possess a quality that even the most advanced lithium-ion batteries cannot hope to match: charging speed. While a contemporary lithium-ion battery requires at least 20 to 30 minutes for an 80% charge, aluminum-ion batteries can achieve a complete charge in as little as 5 minutes, and crucially, they do so without significant heat buildup. This could remove one of the most significant obstacles to the broader acceptance of electric vehicles. The exceptionally fast charging ability of aluminum-ion batteries is a result of their core properties. Aluminum ions travel through the electrolyte 3 times more quickly than lithium ions. Consequently, charging is not only swifter but also preserves optimal performance without putting stress on the battery's internal structure. More importantly, these batteries provide superior thermal stability, effectively solving the overheating problem that is a major weakness of traditional lithium-ion batteries. Due to these qualities, aluminum-ion batteries are not only quicker to charge but also safer and more resilient over their lifespan. Additionally, one of the persistent problems with lithium-ion batteries, the growth of metal dendrite crystals, is practically non-existent in aluminum-ion batteries. Dendrites are metallic crystals that can form during charging, potentially puncturing the separator, compromising the battery's integrity, and leading to severe problems like reduced capacity or even fires. With aluminum-ion batteries, the release of aluminum ions is far more uniform and stable, almost eradicating the risk of dendrite growth. Research from esteemed institutions like Stanford University has demonstrated that these batteries can endure tens of thousands of charge cycles. Without this problem, a massive improvement over traditional lithium-ion batteries. While standard lithium-ion batteries typically last for about 2,000 charge cycles before their capacity falls to 80%, which is about 4 to 8 years of regular use. Some independent research indicates that aluminum-ion batteries could reach up to 15,000 cycles. This suggests that with proper care, an aluminum-ion battery could have a lifespan of up to 35 years, a true game-changer compared to today's battery tech. The basis for this incredible durability is found in the physical and chemical characteristics of aluminum. Physically, aluminum is an incredibly sturdy material, widely used in modern vehicle frames for its strength and resistance to damage. Chemically, aluminum is much more stable than lithium, whereas lithium reacts easily with oxygen and water, causing material decay over time. Aluminum creates a protective natural oxide layer upon exposure to air. This oxide layer serves as a barrier, warding off corrosion and preserving the anode's stability, thus extending the battery's life far beyond what current technologies can offer. This is the crucial point. Tesla isn't just creating a battery that charges more quickly, it's engineering one so durable it could outlive the car itself, making battery replacements a relic of the past. But there's more. Another ongoing concern with lithium-ion batteries is the danger of fire. Lithium batteries can catch fire if they are damaged or overcharged, and the smoke produced is not only poisonous but also notoriously hard to put out. Despite many years of development, this risk has never been fully eliminated. In stark contrast, aluminum-ion batteries are almost impervious to this risk thanks to their stable chemistry and excellent heat resistance, establishing a new benchmark for safety in the EV industry. Moreover, aluminum-ion batteries provide a strategic benefit. Exceptional recyclability. Aluminum is the most common metal on Earth. If this technology is adopted widely, it could dramatically lessen our dependence on costly and difficult-to-source metals like lithium, nickel, and cobalt. Lab experiments have already demonstrated that up to 80% of aluminum fluoride salts can be reclaimed, with projections for even better rates at an industrial level. Impressively, the solid aluminum foil from these batteries can be reused almost immediately after cleaning, positioning aluminum-ion batteries as one of the most sustainable and eco-friendly solutions the sector has ever witnessed. However, no technology is flawless at its inception, and aluminum-ion batteries are no different. One significant challenge is their diminished performance in low-temperature conditions, which currently restricts their application in colder regions. Still, this is not an unsolvable problem. Top research groups globally, including Tesla's, are working intensively to resolve this issue to ensure that aluminum-ion batteries not only lead in performance but are also prepared for all real-world scenarios. At present, aluminum-ion batteries have not been widely promoted and are seldom covered by mainstream news outlets. However, if Tesla can successfully bring A1 battery cells to market and integrate them into its more affordable vehicle lines, it would represent not just a technological feat, but a paradigm shift for the entire electric vehicle market. According to inside reports, Tesla intends to manufacture all its aluminum-ion batteries in the US at a newly expanded site next to Giga, Nevada. The production line is slated to commence operations by the end of this year, once all machinery is installed and calibrated. In principle, the longevity of aluminum-ion batteries is truly astounding. No battery is eternal, but with the capacity to reach up to 15,000 charge cycles, aluminum-ion batteries could last for 35 years or even longer, a number that lithium-ion batteries can't even approach. This makes them a perfect solution not just for EVs but also for large-scale grid energy storage. Crucially, regarding cost, experts believe that with mass production, the price of aluminum-ion batteries could be on par with, or even cheaper than, current lithium-ion phosphate batteries, a prospect once deemed nearly impossible. Over the last couple of years, lithium prices have been on a wild ride, with short-lived drops followed by steep increases. This year, they climbed to $9,000 to $100 per ton. The problem is not just the price but also the rarity. Global lithium reserves are pegged at about 89 million tons, almost 18 times less than aluminum. More worryingly, the bulk of these reserves is located in only 4 nations. China has about 16.5%, with the remainder mostly in the lithium triangle of Chile, Bolivia, and Argentina. With such a consolidated supply, lithium prices are not only elevated but also highly susceptible to geopolitical pressures.